And actually, as you go through in math, you'll do more with medication or dispersion of some kind of drug or medicine throughout the body using calculus or differential equations. So at some point, I hope to talk about this, but calculus actually helped with HIV and finding treatment for that, which is cool. That'll be down the road, but so this, I don't know, I think it's fascinating. You know, math kind of describes everything around us, and why not how your body works too. I kind of call it the language of the universe, which is kind of neat. It looks kind of nasty, the equation I mean. It does say that C is a constant, so that makes this just a number, and M, the amount of medicine absorbed in the blood. So if we kind of read through all of this, really we're just trying to find the derivative of this function. So and maybe I'll do it here. What is the variable we're differentiating with respect to? Yeah. Yeah, did you say that? Okay. So remember that it's not always just dx. And if you're doing an FRQ where you're writing it out and it was supposed to be dr dm, but you're in the habit of writing dr dx, they would take a point off because it's technically incorrect. So do be careful with your with respect to variable. So dr dm, excuse me. So reaction as a function of the amount of medicine. I'm going to underline this. All right, well, what rule are we applying here to do this, first of all? Yeah, so if we look at these as two separate functions of m being multiplied, then we're doing the product rule. And general product rule, so of u times v. You guys remember how it looks? Oh, good. Plus, good. Nice, good job. So good, even though, you know, we've assessed now on the product rule, we will need to have that be just right there, ready to go anytime we need it. So, in this case, c over 2 minus m, that looks messy, minus m over 3, that's v, and then du dx is just 2m, du dm I should have said, okay, plus m squared. And then what's the derivative of that thing? Yeah, so remember this is just a constant. So the derivative of it is 0. And this is really negative 1/3 m. So when we take the derivative of that, it's just negative 1/3. And then we can kind of clean up a little bit. If this was an FRQ, would you stop there? Could you, I should say, stop there? Okay. So probably that, because it's a context problem, those are most likely going to be, or that's a good chance of having it be an FRQ. All right. Here we could distribute and get 2m, why is this freaking out? 2m squared over 3. So take off of 1, and we just get an m squared over 3. So this is, guys, I don't know what the problem is here, but 2mc over, actually just mc over 2. mc over 2, so that's that term. My fault, it's just mc. And then again 2m squared over 3 negative, and then another m squared over 3 negative, so minus 3m squared over 3, which is mc minus m squared. And we simplify that all down. Did anybody take it that far? Which is a lot easier to plug into than the first one. However, if we were asked to evaluate this at some initial concentration of the medicine, where would you plug that in? Like, would you get it all the way down to mc minus m squared and then plug in, or plug it in right after this first purple step? What do you think is better?
Probably do like the purple because it's easier to work with numbers.
Right. I agree. And of course, in that case, we'd have to be given a value for c as well, but all of this would become just a number. So as soon as you can, it's better, and that's what we're going to talk about today a little bit. Cool. Any questions on that one? Okay. All right, well, chapter 3 includes another rule, a hugely important rule called the chain rule. So building on the rules that we learned last chapter for derivatives and differentiation. And this is a very short unit, or like 6 sections to it. So the next one is kind of unrelated, it will feel like a little bit, but it's implicit differentiation. So we're kind of taking these derivatives a little bit to the next level before we start applying them in the next section, in the next unit. So calculate derivatives of compositions of differentiable functions. And I kind of like the chain rule name because it just chains things together. So it kind of makes sense. Let's quickly review composites. And all 3 of these are a version of that. Composite, remember, means a function inside of a function. And that could continue on. So we could have, like, this one has 3. Okay? So you'll notice down here we use f and g. As usual, also have notation using other variables. Just depends which notation you use. So in this case, what is the outside function? Or the first function, if you want to think of it that way? Just sine of x, okay? And then the inside is x squared. So we're just making sure we see the 2. How about this one? And this one has 3. Yeah, this time I'm going to use letters. Okay. So if you think about what we will eventually need to differentiate all 3 pieces is really the idea behind the chain. Okay? Are you guys still sticking primarily with the prime notation? All right, how about you? You said at one point you like Leibniz better.
Yeah.
Still do?
Yeah.
Okay. Let's write both. And I guess keep using it, but as we've seen, there's cases when you want to be able to use both for sure. All right, so we have some g differentiable function inside of an f. So the chain rule says f prime of g of x, not minus, times g prime of x. So we're going to pretend like this inside is just a chunk and differentiate f. And then we can differentiate the chunk that's inside. Does that notation make sense to everybody? Okay. I think that's helpful and fine. I also do like the other notation, the other version of this. So f of u, you're going to see this idea of u substitution. We've already seen u used as well. And then u is a differentiable function. So we're going to have df dx is df du times du dx. And this could continue if we had like this cosine sine 5x, then we'd have to add in maybe v. So this would say df du, du dv, dv dx. And we'll see that down here as we go. Okay? So either one is fine, whichever one makes more sense to you. So on these first two, let's make sure we're identifying f and g. So what is f of x in this case? And then g, x squared minus 5. Okay? So f prime of x. What do we do first? So looking at this version, we need to differentiate f. So 4x to the third, but x is g, right? So x squared minus 5 to the third. So we keep g inside of it as if it was the x. All right, and then times, now we can differentiate g of x, which is 2x. And we could clean that up just a little bit by saying 8x, x squared minus 5 cubed. How's that feel? Okay, so I want you to think of this as working outside in. That's kind of what we're doing, right? Differentiate the outside, ignoring the inside, then the inside. And let's see this one with the other notation. So we have g of u is u square rooted. U is 4x minus 3. And partially I want you to start thinking of it this way as well, because u substitution, I know I've said that multiple times, is a pretty powerful way to do integrals as well. And you call something u, and then deal with everything around it, and then plug u back in when you're ready. Okay, so this is dg dx. I'm going to write it out first, dg du times du dx. So dg du, we are differentiating, just like I mentioned in the warm-up, where we had to be careful with what we're differentiating with respect to. In that case it was m. We are differentiating g with respect to u. Who cares what u is for this part, right? So what is the the derivative of square root of something? You guys have that one memorized? Okay, 1 over 2 root whatever it is, okay? And then du dx is just 4. Well, you could skip this line that I just wrote and just substitute u, which is 4x minus 3 right in there, okay? I just wanted you to see the symbolism there. 4x minus 3. Okay, and then of course we can simplify that, but I'm running out of room, to 2 over square root of 4x minus 3. Okay. Now this one, tell me about it. How many functions do we have there? What did you say? 3. Do you guys see 3? Okay, what are they?
Square. What would be your outside one?
Yep. So h of u is u squared. I'm just going to pick whatever letters, so, and then u is sine of 5x, and v, actually I need to say sine of v, sine of v, and then v is 5x. I'm still going to do this notation again, okay? So dh dx, in symbols first, is dh du times du dv times dv dx. Everybody follow? Working outside in. Okay? So dh du, what is the derivative of u squared? 2u. Okay? And then du dv, what's the integral of sine of v? Cosine of v. dv dx, what's the integral of v? 5. Okay, now we got to go plug in what u and v are. So this becomes 2 times sine of 5x times cosine of 5x times 5. I don't really need those parentheses, I guess. Maybe just on 5x. Like that. Okay, and then we can clean that up a little bit. 10 sine 5x cosine 5x. How does that feel? Is that okay? There's a lot of places where you can get mixed up. So make sure you're using a notation that works for you. Okay? Do you want to redo that one with the prime, or is this okay? Yeah, do it? Okay. That was h, so. Alright, so we have h of x is x squared. And then I guess I'll cycle back to f. F of x is sine of x, and g of x is 5x. So h prime of x is h prime of g prime of, f prime is next. H prime of f prime of g prime of x. Like that. It's a lot of things, right? So we go back to this. So 2x for our first h prime. And then inside of that, we have the sine of 5x times, then we have to do f prime, which is cosine of 5x. And then g prime, which is 5. And then same cleanup. One thing I don't like about this notation is this x represents 5x inside of sine inside there. And it doesn't show that quite as clearly. So, but it works, it's fine. Okay. All right, how about this one? Do you guys want to try those two? They're the same, and that's okay. You want to give it a shot? Okay. Let's see. So dy dx. Did you guys do primes or dy's on this? Okay. Yeah, this one kind of sets up for that. I think it's nicer in general, but anyway. Is dy du times du dx. What is, so this is the derivative of natural log, which is what? Excuse me. 1 over u times Now du is x cubed, so 3x squared. So this is 1 over x cubed times 3x squared, which is just 3 over x. How'd that go doing it that way? Okay, and then this one, it's the same problem, but just remembering the log rule. So we could rewrite y as 3 natural log of x with that log property, the property of logs, I mean. And then just to take the derivative like normal, you don't have to use the composite chain rule now. So 3 is a constant, so we just leave that, and then derivative of natural log is just 1 over x, so 3 over x. Either way, just keep an eye out for those opportunities to save yourself some work. All right, this one looks kind of nasty. Tell me what you think of it. You're right, it should. Let's change it. And then, Aiden, what did you say?
So it's a quotient rule inside the chain rule.
Yep, quotient inside of chain. So, why don't you give it a shot? I'll just give you this advice that the quotient rule will be your g prime of x, right? Or your du dx. So it's a little bit longer because of that. Alright, so just got it set up here. So u cubed, that's an easy one to differentiate. So we get 3u squared. And then the big one here again is the derivative of u versus t. So that inside part. So tell me about the product, or excuse me, the quotient rule. Do you remember the little saying for it? Yeah. Low D high minus high D low. Good. Excuse me. So 2t minus 5 times 2t minus t squared plus 1 times 2 all over 2t minus 5 squared. Alright, so if this was an FRQ, you could stop there. But I could totally see them putting this on a multiple choice and having to manipulate with algebra to make it match. So what all can we do? What?
T squared plus 1 over 2t minus 5
Oh, here, yeah, I do need to do that. How about, let's simplify this first. Minus 2t squared minus 2. This looks tempting to try to factor, so I suppose you could, but it doesn't, but you could. I mean, you could look at trying to do something like that in these cases, right? Okay, what else can we do? What's that?
Like if you take the square, like the t's, like if you put it to the top and bottom, you can
Yep.
combine.
Let's factor a 2 out of here. Okay. All right, anything else? It's not going to get a whole lot prettier. We could make this be a fourth power. 6 t squared plus 1 squared, t squared minus 5t minus 1. I don't know if that's much better, but there might be an option on the multiple choice, whereas the previous steps were not, right? So just, I get it, like I get that calculus uses algebra 2, maybe some pre-calc a lot, but also if you miss the point on this because of algebra, that would be annoying, probably too. Any questions on those? Okay, and then a little different version on the back where we're plugging in a number. So write yourself this advice. Plug in that this is what we talked about from the warm-up. Plug in the number as soon as possible on these. This is advice, it's not a requirement. So if you're somebody who likes to do algebraic simplification first, that's okay, just be careful. All right, so what's our function this time? Well, before I say that, do you see how this is product rule, chain rule?
Yeah.
So I guess before I start doing the U stuff, let's identify that. So how do we do this one? Okay. Okay. So 1 square root of 1 minus x times 2, that's du prime, plus 2x, and then 1 over 2. Let's be careful here. So that's going to be du, d whatever we call that, df du. So 1 over square root of u. I'll put the u out there in a second. And then times du dx, which is negative 1. Okay, and then u equals 1 minus x. I need to plug that right there. I think I'll do that on the next step when I simplify. Does everybody follow how we got to that point? Excuse me. So this all becomes 2 times negative 1. So plus negative 2x over 2 root 1 minus x. Oh, see, I have the habit of doing algebraic simplification. I've just wrote this note, but I'm an algebraic simplifier. So should I do that? No. What should I have done? Just plug x in, right? And just do it from there. Okay? Yeah, I have always been that way, I think. I like the algebraic part. So g prime of negative 3, we can just start plugging that in here. So 1 minus negative 3 times 2 plus 2 times negative 3 times 1 over 2 times 1 minus negative 3 times negative. Okay. And all of this is doable without a calculator for sure. my point in saying that is you wouldn't have to have one. Like this could be a non-calculated part. Alright, this becomes square root of 4 times 2, which is 4, plus negative 6 times 1 over 2 root 2, so times 1/4, times negative 1 makes that plus. So 4 plus 6/4, what is that? 8/4 plus 6/4. Sorry, that's not 8/4. 16/4 plus 6/4 is 22/4. Or 11 halves if we simplify it. Okay, so definitely plug in your value first. Alright. So let's stop there and we'll pick this up tomorrow. I think these kind of problems are kind of fun. So that'll be where we start.